In our last section, we looked at exponential functions and their graphs. So I want to review just a second the exponential function 2 to the x. And we do our chart, just in case we don't remember what this looks like. If we let x equal -2, we get 1/4, because this is 2 to the -2, which is 1/4. If we let x equal -1, we get 1/2. If x is 0, we get 1. If x is 1, we have 2. And if x is 2, we get 4. So that graph crosses here, this point, and it looks like this. We have an increasing function. We have a domain of all real numbers, a range 0 to infinity, and notice it always crosses at the point 0, 1 unless we've done some kind of a shift with our graph or with our function. Now I want us to look at what the inverse of this function might be, because this is a one-to-one function. Even though close to the x-axis it looks like it wouldn't pass the horizontal line test, we can't draw it exactly the way that it should be. This is a one-to-one function, so this one-to-one function does have an inverse function. And if we switch the x and y, we get x equals 2 to the y. Now that's not something that we're used to seeing. We don't know how to solve this function for y, but we can graph the inverse function. So I want us to go ahead and graph the inverse function, and I'm going to change the color for that. And so let's see what for the inverse. We don't have it defined yet. We did solve it for x, but we haven't solved it for y. But let's just look and see what the inverse function looks like. The points are going to change, and we're going to have 1/4 -2, 1/2 -1, 1 0, 2 1, and 4 2. Once we have the original graph, it's very easy to graph the inverse. So I'm going to start with this point, and I've got 2 1. Those are a little bit easier, and 4 2. And we're going to be very close to the y-axis. So here is the inverse function. Notice our inverse function is also an increasing function. It is one-to-one. Its domain and range switched places. For our original function, our domain, it was all reals, and our range was 0 to infinity. We said it was one-to-one. It was increasing. The horizontal asymptote was y equals 0. Notice for the inverse function, it's still an increasing function. It's one-to-one. This time the domain is from 0 to infinity, and the range is all real numbers. This passes through the point 1 0 instead of 0 1. And we don't have a horizontal asymptote. Now we have a vertical asymptote, and that vertical asymptote is the equation x equals 0, or the y-axis. Also, if we were to graph the equation y equals x, we can see that the functions reflect across the line y equals x. Now we said that when we algebraically tried to find the equation for the inverse of 2 to the x, f of x equals 2 to the x, we got x equals 2 to the y. Well, instead of leaving the equation like that, we're going to express this as a log. And we get the log base 2 of x equals y. That's the same thing as this. The log base 2 of x equals y. In calculus, we used to always say that a logarithm is really an exponent. Log base 2 of x equals y is how we read that. Just in general, if we have base a, we define y equals the log base a of x as the number y such that x equals a to the y. That's why we say that a logarithm is an exponent. Notice the exponent is right there. All right? In this case, x has to be greater than 0, and a is positive. It cannot be equal to 1. Okay, a is positive and it cannot be equal to 1. So if you had well, the base has just got to be positive. Let me just say that. The base has to be positive. Okay, we're going to convert from an exponential equation to a logarithmic equation. Notice I have an exponential equation, and we have said that a logarithm is an exponent. A logarithm is an exponent. That's because this is just another way of writing a to the y equals x. The base to the y equals x. So if I want to write 16 equals 2 to the x as an exponent, we would write this log base 2 of 16 equals x. A logarithm is an exponent. If I had 10 to the negative 3 equals 0.001, and I want to write this as a logarithm. Remember, we said a logarithm is an exponent, so we're going to have this by itself. Log base 10 of 0.001 is equal to negative 3. If I had e to the t equals 70, if a logarithm is an exponent, then I could rewrite this as log base e of 70 equals t. Another way we could write this is the natural log. The natural log is base e, and we don't have to rewrite the e. And if you'll notice on your calculators, on your graphing calculators or scientific calculators, you do see an ln. That is the log called the natural log with base e. I could also rewrite log base 10 as simply the log of 0.001 equals negative 3. This is the common log. If you don't see a base, then that's the common log, which means it's base 10. The natural log is base e. And most of the formulas that you're going to be working with or applications are either going to use the common log or the natural log. So on your calculator, you have the log. That has base 10. You also have ln, which is the natural log, which is base e. You don't have to repeat the 10 with the log, common log, or the e when you're using the natural log. All right, now we converted from an exponential form of the equation to a logarithmic form. Let's go the other way. Let's convert from a logarithmic equation to an exponential equation. Here we have log base 2 of 32 is equal to 5. Well, I can rewrite that as 2 to the 5th. A logarithm is an exponent. This becomes the exponent equals 32. And that is a true, I mean, we can check that. We know that that's true. If I had the log base a of q equals 8, and I want to rewrite that as an exponential equation, that's a to the 8th equals q. Just one more, just so you see plenty of practice. X equals log base t of m. I can rewrite that as t to the x equals m. So it's very easy to convert between a logarithmic equation to make it exponential or vice versa. Now, using that idea, I want us to find the value of some logs. Now, if I have log base 10 of 10,000, that's the same thing as the log of 10,000. I don't have to put base 10 if it's base 10. If I just have log, it's understood that that's base 10. But if I want to see what this is equal to, what I'm trying to find out is 10 to what power is equal to 10,000? Well, if we rewrite 10,000 with base 10, we get that is 10 to the 4th. So we know that the value of this logarithm is 4. Let's look at the log of 0.01. Again, this is base 10, so I don't have to write base 10. To solve this, I'm going to rewrite it as an exponential. 10 to some power is equal to 100th. Let me write it like this, so maybe we can see how to redo that. Well, I can rewrite that with base 10 as 10 to the negative 2. So in this case, we see that the log of 100th is equal to negative 2. Just to do a little bit more with some different bases, let's look at the log base 2 of 8. Well, I can rewrite that as 2 to the y. If you want to use x, you can use x, but 2 to the y is equal to 8, which we know is 2 cubed. So in this case, this is equal to 3. That is the exponent. I think I'd rather have the white. All right, let's do, this one's a little different, log base 9 of 3. That's equal to something. If you want to go ahead and write an equation, you can do that, so it makes it a little bit more sense. 9 to what power equals 3? Well, if we rewrite this as 3 squared, we know that 3 has an exponent of 1. If we set 2y equal to 1, then y is 1/2. So the log base 9 of 3 equals 1/2. And you can always check it. Does 9 to the 1/2 equal 3? Well, the square root of 9 is 3, so that checks. Here's your answer. Okay, just a few more. Let's think about this one, log base 6 of 1. Well, 6 to what power equals 1? Anything to the 0 power is always going to be equal to 1. So in this case, this is equal to 0. Anything to the 0 power is going to be 1. So 6 to the 0 is 1. And let's look at the log base 8 of 8. Well, 8 to what power equals 8? In this case, we know that that's going to be 1. If these two numbers match, it's always equal to 1. And if this number is 1, it doesn't matter what the base is, it's going to always be equal to 0. So those are some properties that will always hold true, that the log, no matter what the base is, of 1 equals 0. That's a very good one to remember. And also that the log of a base, if these numbers match, that's always going to be 1. And this is for any logarithmic equation, base A. It could be base 10, base 2, the natural base, but these properties will always be true. Now, we've already seen that there are some values for the logs that we can calculate without a calculator, but there are many more that we cannot calculate without a calculator. So I plugged these into my screen so you could see what it should look like. On your scientific calculator, if you see the log without a base, it is talking about this key. That's what I put in. The log of 45 we see is 1.653. It keeps going on and on. Now notice the log of -2, we got an error. That's because the domain for the natural logs was 0 to infinity. If you have a positive base, there's no number that you can raise that to and ever get a negative number. The domain was always positive, so that's why this value is an error. The answer would be that just the log of -2 does not exist. Same thing with the natural log of -6. The natural log of -6, and I put it in parentheses because it's a negative, does not exist. And the natural log key is underneath the log key. That's the base E. For the natural log of 45, it's not the same as the log of 45 because you have a different base. That was 3.806666249, and it would keep going on and on and on. So that's how we can use our calculator to find the values of logs and natural logs. All right, I didn't know I hit record, but this has been recording for a minute or so while I was writing it out. We have this problem says a model for advertising response is given by n of a equals 1,000 plus 200 times the natural log of a, where n of a is the number of units sold in thousands of dollars. How many units were sold after spending $1,000? In other words, a is equal to 1. If you spend $6,000, a is equal to 6. Well, let's see what we can determine here. If a is 1, we're going to have 1,000 plus 200 times the natural log of 1. Now, what did we say about the natural log of 1? The natural log of 1 is always 0. So this is simply going to be 1,000 units. Not dollars, but units. 1,000 units were sold. Didn't even have to get a calculator out on that one because we know that the natural log of 1 is always 0. You see that one comes up a lot in calculus too, if any of you happen to take calculus. All right, let's do a second problem here. Same example, same equation, but this time, what if we spend $5,000? If we're spending $5,000 in advertising, then A is 5. And we are going to find n of 5, which is going to be 1,000 plus 200 times the natural log of 5. And if you just type that into your calculator, you should come up with 1,322 units. Straight into your calculator. So be sure that you read the question carefully when you've got, I think I just gave you one application. But notice you would not have gotten the same answer had you not recognized that A is 1 and here that A is 5. You can't use the 5,000 in this case. So read the problem to see if there's some kind of hint in what you're doing. All right, the assignment here is, this is assignment number 3. And it's page 345, 3 to 57, every third, 67, 79, 81, and 96. Now you have a couple of questions where you are asked to graph the exponential and the logarithmic function. I always graph the exponential function first because that's a little bit easier, and then I graph the logarithmic function. Right?